Welcome to Monday Night Calculus. My name is Curtis Brown, and I've got with me Steve Kokoska and Tom Dick. I'm very excited to have these guys here this evening. Really excited to be bringing you guys the last of our Monday Night Calculus series for the spring of 2023. Steve has prepared a whole bunch of great questions for you tonight. I know Tom's got some good technology tips and things. So just a couple of notes of housekeeping. First of all, I want to make everyone aware that we are planning to continue doing this again in the fall. We have a tentative schedule penciled out, but we'll be posting that in the Calculus Teachers Facebook group, along with we'll probably be sending an email blast to our TI folks who have our email addresses, as well as I will be getting back into the YouTube channel here and putting that schedule out here in the next several weeks, so that you guys can know just what we're planning to do in the fall, and we will be running these again, similar concept, starting again in the fall. Stick around to all the way to the end, and I will give you some information about how to get professional development certificates. Otherwise, I will turn it over to Steve.
Thank you very much, Curtis. Let's see if we can share this, see if this works. How's that looking? Okay.
Yeah, I think so.
Okay. One other little thing for the fall too, Curtis, I think maybe we should mention is that we're looking for topics that teachers and our students would like us to talk about. So if you have something, maybe they could send that, or either post it on Facebook or maybe send you an email, and we'd be happy to consider that as a topic where we, again, come up with some good review questions and discuss those questions on Monday Night Calculus. Well, this is a BC topic tonight, Curtis, and I hope you've done your homework. There's a lot of little details in here, lots of things that I'm going to have to ask you about. We're going to talk about radius and interval convergence of power series, and we've got 4 good problems to start out with here in number 1.
I did not do my homework either, Steve.
Well, oh boy, it's going to be awful then. We've got some good...
Hopefully Wanda did her homework, and Mark.
And she can help you, and they can help you.
They can help me out a little bit in the chat.
Well, we've got some good analytical, I think, solutions. We've got some good technology solutions. And I also think along the way, we might have a couple of good exam tips. The exam is coming up here in just a couple of short weeks, so maybe a couple of tips to help your students get some extra points. So the way that we're going to attack these first few problems is by using the ratio test. Remember, the ratio test is used to actually show absolute convergence, but we know that if a series is absolutely convergent, it is convergence. So this is the general technique that we use in order to find the radius of convergence, and then from that result, we move on to find the interval of convergence. So let's take a look at this first one. We've got this power series given right here, and I'm going to start out by taking a look at the ratio, the absolute value of the ratio, a sub n plus 1 divided by a sub n. Now, Curtis, I usually do these in a two-step process. And by that, I mean, I usually take a look at this absolute value of the ratio and simplify as much as possible, and then take a look at the limit. I'm going to scribble a little bit out here. You can, of course, excuse me, start this all by taking the limit as n goes to infinity out here. But what happens frequently with students on the exam is they will write this limit notation only once. And of course, it must be written continuously until you actually execute that or take the limit as n goes to infinity. Now, there was a time when some chief reader said, well, as long as we see the limit as n goes to infinity once in the process, we will accept that. But that's very dependent upon the chief reader. And I would suggest that in this era where we're stressing good communication skills, that notation might in fact be necessary throughout the whole process if you elect to do it this way. So I think a good idea is to work with the absolute value of this ratio and simplify as much as possible. Now, I've done a couple of little things here. I've actually taken the reciprocal and multiplied And I've tried to do a little simplification. Since I've got an absolute value symbol here, I don't have to worry about those minus ones. And let's see what happened here with the fours. I have a 4 to the n plus 1 in the denominator, a 4 to the n in the numerator. So there's a 4 down there. There's going to be a lonely x left over up there in the numerator, and I've got an n squared over n plus 1 squared. And I elected to collect these terms like that. So now I'm ready to take a look at the limit as n goes to infinity of this ratio. I plugged it in there, and I am skipping a couple of steps here, which I believe would be acceptable on the AP exam, but you might consider putting in an extra step. As n goes to infinity, of course, this is constant 1/4. And although it looks kind of funny, the absolute value of x is constant as n goes to infinity. And so this is the only term we really need to worry about. What happens to that as n goes to infinity? Well, I skipped a step here that does indeed go to 1, but what's sort of a classic way to show that, Curtis? Do you know by any chance how I would do that? How I would show that this expression, the limit as n goes to infinity of n squared over n plus 1 squared, how would I show that that's equal to 1? Any ideas? There's a couple of ways maybe that I could do this, but one sort of classic way to do this without L'Hopital's rule. Any ideas on that one?
Well, I'm just thinking about it. You kind of sense it out a little bit, because if you do have that, you have n squared over n squared, the rest of that as n gets really, really large kind of just becomes relatively small comparatively to n squared. And so n squared divided by n squared approaches 1.
Very good, sure. And I think the classic way to do this is to divide both the numerator and the denominator by the largest power of n in the denominator. So we divide top and bottom by n squared.
Right.
Now, again, I don't think you need to show that on the AP exam. So that goes to 1. And so this limit now is 1/4 times the absolute value of x. Don't forget the absolute value in there. So in order for this to converge absolutely, that limit would have to be strictly less than 1. That's the result of the ratio test. And so I'm going to solve that and find that the absolute value of x must be less than 4. Now, a word of caution here as you prepare for the exam. If you're asked to find the radius of convergent, this boxed in expression is not sufficient. So you must somehow state that the radius of convergence is 4, or we accept this sort of notation. We understand that in the context of this problem. So I know the radius of convergence is 4, and in order to find the interval of convergence, I must check the 2 endpoints. I see that this series is centered at x equals 0. So that means I need to check at x equal -4 and x equal +4. So what I do is I take x equal -4 and I go back to the original series up here and plug that in. And if I haven't made any mistakes here, I think the minus signs, we're actually going to have a -1 to the n times another -1 to the n. So that's going to be -1 to the n plus n 2n. So that's always going to be positive 1. The 4 n's will cancel, and I'm just left with 1 divided by n squared. So in the context of this kind of a problem, the student it would certainly be acceptable to say that this series converges because it's a p series with p equal to 2. And you could add in there that that's greater than 1 if you wanted to, but you don't have to. So what happens when x is equal to 4? I do the same thing. I plug in, I get a little cancellation of the 4 to the n's, and I'm left with this series. Well, if you stare at that long enough, you'll recognize that that one converges. And we recognize this abbreviation in this context. It converges by the alternating series test. It would be nice if you showed us the conditions of the alternating series test, but in this kind of a problem, you wouldn't have to. So that means the interval of convergence here is -4 to 4 closed. And that's a nice problem to start out with. Sorry, Curtis, there's an awful lot of writing on that page. Okay, any questions on that one?
I haven't seen any questions or comments come in.
Okay.
And if I make a comment, Steve, on that one?
Please.
So up higher in that problem, you had an absolute value of x less than 4. And if for an open interval of convergence, that would be an appropriate way to express the interval, if I'm not mistaken.
Yes, the interval. Yep, correct.
I just wanted to point out that let's suppose that you had a problem where when you check the endpoints, it actually diverged at both of them.
Right.
Then your interval of convergence, you've already got it up there with absolute value of x less than 4. But folks should realize, though, that even if that turned out to be the interval of convergence, they're really going to want to see that you bothered to check the endpoints individually.
Gotcha.
And of course, on this one, it was super critical because you needed to include those endpoints. But they're going to want to see that check of the endpoints to get full credit for the problem, even if it turned out you didn't keep either one of them because it diverged there. So.
Gotcha.
All right. Pardon the interruption.
Oh, very good. Excellent. Okay. Let's take a look at this one. Okay, so let's see. The sum from n equal 1 to infinity, x plus 1 to the n over n5 to the n. So let's see. This power series is centered at -1. I'm going to start in the same manner. I'm going to take a look at the absolute value of that ratio, a sub n plus 1 divided by a sub n. And I'm going to quickly take the reciprocal of the denominator and multiply. And let's see, don't let me make a mistake on this one. I think we've got a lot of cancellation. Once again, I'm going to have a 5 left over in the denominator. I think I'm going to have an x plus 1 left over in the numerator, and I think I've got an n over n plus 1. Okay, so same sort of thing here. I'm going to try to not collect terms, but write this in a nice way, in a judicious manner. Here's the absolute value of x plus 1. These terms are always positive, so they can pass freely through the absolute value symbol. And now I'm ready to take a look at the limit as n goes off to infinity. And once again, these two terms are constant as n increases without bound. And this one, for a similar reason, goes to 1. I can divide both the top and the bottom by n and see that that goes to 1. And so I'm left with this as the limit. So by the ratio test, if I want this series to be absolutely convergent and therefore convergent, I force that limit to be less than 1. I solve for the absolute value of x plus 1, that's less than 5. And so the radius of convergence here is 5. Beautiful. Now, in order to get the interval of convergence, I still need to check the two endpoints. So remember, this series is centered at -1. So -1, -5. I've got to take a look at an x equal -6. I plug that in. And Curtis, don't let me make a mistake here, but I think this becomes the alternating harmonic series. I think the 5 to the n's cancel, and I'm left with a -1 to the n in the numerator. And again, I believe that this would be perfectly acceptable for a student to write. It converges because it's the alternating harmonic series. That would be okay. I'm going to plug in an x equal 4. And when I do that, let's see, the 5 to the n's cancel, and I'm left with, son of a gun, the harmonic series, which we know diverges. And again, this would be acceptable to write. And so I believe here, again, thinking that, remembering that this power series is centered at -1, the interval of convergence would be -6 closed to 4 open. How about that? I think in many of these problems, again, in thinking about the AP exam coming up, Tom, correct me if I'm wrong, many of these problems are worth 5 points. It's an awful lot. Often it's BC6, not all the time. There are often 3 points associated with this work here. Often there is 1 point associated with setting up the correct ratio. there is 1 point for finding the limit of that ratio, and then 1 point for correctly identifying the radius of convergence. So there's 3. And then 1 point usually for checking the 2 endpoints. We usually separate this in the following way: 1 point for checking both the endpoints, and 1 point for correct arguments. So it's not like 1 point for checking x equal -6 and the correct conclusion, and 1 point for x equal 4 and the correct conclusion. It's 1 point for checking both endpoints and 1 point for the correct conclusions. And of course, producing the correct interval of convergence. Beautiful. Tom, a little technology.
Sure. Yeah. let's
Okay.
give it a shot.
See if that works. There we go.
All right. So I'll share my screen, hopefully, and let's see if this works. So you all seeing a
Inspire.
screen there? Okay.
Yes, sir.
Great. All
Yes,
right.
sir.
That little title screen there. Okay. So what I've done here on the Nspire is just gone ahead and defined a couple of functions that are going to represent, well, it's not exactly the power series. For example, in part A, the power series that Steve was illustrating for us was from n equals 1 to infinity. And notice I've replaced infinity with k. So we can think of this as kind of like a partial sum for the power series. And the power series, it's a function on the interval of convergence. We can treat it just like a function. And of course, this partial thing, that's a function for all x. But what we want to do is get a sense for what does that interval of convergence really mean? What's that talking about? So I've replaced infinity with a k, and then on a graphic screen, we're going to graph this partial power series and then see what happens as k gets bigger and bigger. Now down here for part B, this was the second one that Steve did. So we're going to take a look at both of them. But let me start out with A first. And you can jog my memory, Steve. I think he said the interval of convergence on that one was from -4 to 4 closed.
Yes, sir. -4 to 4 closed. Yep.
-4 to 4.
Great.
Closed
Okay,
interval.
so I'm going to go to the graphic screen. There we go. And you can see I've got f1 of x is a of x. That's that power series thing with k equal to 1. So that would really be just the first term. Now I'm going to go back and just take a quick look at it. If we went from n equals 1 to 1, what would we get? Well, we would just get one term, and it would be with n equal to 1. So let's see, -1 to the 1, that'd be -1. X to the first, well, that's just plain old x. N squared is 1, and 4 to the 1 is 4. So I think when all the dust clears, I'm just looking at -x over 4.
Mhm.
And if we go to the graphic screen, that's the graph I've got. That's -1/4 x. So, but as I increase k, okay, now this is the sum of the first two terms of that power series. And so that's going to be a quadratic because now we've got that an x squared involved.
Mhm.
And then we've got a cubic, and then a quartic, and then a fifth degree. And, I think I'm going to bring up the menu, bring up geometry. And let's do the points and lines. I'm going to do a segment. And just to help us, I'm going to mark an interval from -4 to +4. A little bit sluggish here. Let's see. There we go. So there's that interval. And so you can see the two endpoints of the interval, -4 to 4. And as I keep increasing the degree, and I'm calling it the degree, but it's how many, because it corresponds to how many terms. You can see this effect that between -4 and 4, this graph it almost looks like the negative x over 4, just the first term. It's got a little bit of curve to it, but it looks very calm. But outside of -4, to the left of -4 and to the right of -4, as I alternate in degree, positive, odd and even, we can see that it takes off to infinity really quickly outside of -4 to 4. So it really gives us a sense of what that interval of convergence is representing for us. It's a domain over which those values of the power series, when you plug in the values of x from that interval, you get a numerical series that converges nicely. But if you get outside of that interval, you get a divergent series. And this is just kind of underlying that. Okay. Any comments, Steve?
That's pretty cool. It almost looks like it, at least on the right-hand side, it almost looks like it goes to x = 5, doesn't it? Initially, I mean, you must have to go much, right?
Right, yeah.
That's a really, really cool.
Yeah, it's something I would never thought of to do before the graphic technology that was available to us.
I had never seen that or even thought about that in the way that turns up. That's really, really nice.
Also, I should point out, I mean, you guys know I use the TI-Nspire cache. You can see it over here, but this doesn't rely on CAS at all. I mean, you can
you could use this on an 84.
Yeah, I just defined this as a function and a slider. So there's no CAS going on. I mean, if you were actually computing it like a Taylor polynomial or Taylor series, then the CAS would allow you to do some of those computations. But here we just entered the power series that was given to us by Steve. I replaced the infinity with a K, put it on a slider, investigate.
Tom, while Steve's working the next question, you might consider exploring whether this works on the 84 or the transformation graphing app.
Okay.
Using that value A, using the transformation graphing app on the TI-84. This might be a way to do that. I don't know. It struck me that's an idea that you could try.
Yeah, and on a later problem, I am going to show how you could do a similar thing on the 84.
Okay.
It's not the way you just mentioned, though. So I'll be interested in investigating what you just talked about.
So, Tom, 2 questions that maybe we can throw out there to people who are listening, watching. So as K increases, gets bigger and bigger, increases without bound. First question is, what does that graph between -4 and 4 look like? Is there some way you can characterize that or tell us what that might look like? And then the second question is, what happens to that graph across as you cross 4 and as you cross -4? So I don't expect an answer to that right away, but I think that would be something to think about.
Yeah. In fact, I was musing a bit on it, Steve, and just going back to the this original thing. We talked about the very first term is just -x over 4.
Yes.
And seeing this denominator has both n squared and 4 to the n in it. I'm thinking that the additional terms in this shrink pretty fast for values of x that are between -4 and 4.
Yeah.
So I'm thinking that it's not exactly -x over 4 because we do have a few more terms in it, but it's the -x over 4 is the predominant behavior of this function. That these terms really go to 0 fast. So that first term is most of what the picture looks like.
Yep.
That we were seeing between -4 and 4. And we do have convergence at those two. Now, once you get outside of those, man, I think it diverges pretty for large values of K. Yeah, you're gonna, well, it's a diverging for any value outside
Right.
of -4 and 4.
Right.
And we're seeing that graphically where it just zooms up and down, depending on whether it's odd, even degree. This second one this had a slightly different, I think this one had the interval of convergence was -6 to 4.
Right.
And it actually diverged at +4.
Correct.
Remember, so we only had the left-hand endpoint. So I'm going to go back. Thank you for your patience. I'm going to go ahead and just define this. There we go. I'm just going to replace the A of X with B of X. That's what I had stored away for that function.
Mm-hmm.
And we didn't take a look at it, but if you trust me, this is just actually that very first term for K equal 1 is just the very first term is actually just X over 5, I believe. Now I'm going to change this line segment to go from -6 to 4. So I moved that left endpoint over here to -6. And now I just want to increase K and see what happens to the behavior. Now this one, I don't think it had an alternating piece to it. There wasn't any -1 to the end. So you can
That's
see.
correct.
Or did it? Let's see. Was there an alternating piece to it?
No, but there's an X plus 1 to the end.
Oh, right. So we'll have negative values when we're to the left of -6, right? Yeah. Well, we have negative values when we're to the left of -1, I should say.
Yep.
But you can see that as I increase the number of terms in that power series that we're taking in our partial sum, the really well-behaved part of this graph is between -6 and +4. But notice that +4, it is taking off. It's kind of exhibiting a somewhat asymptote looking behavior over there.
Yeah.
Now, for any finite value of K, this function actually is defined everywhere. It's just we're really, what's going to happen as K gets larger and larger and larger is this piece between -6, including -6, and up to and not including 4, we're getting a convergence of those values. But outside of that interval, we're getting divergence of the series. And it's just, I think it's really striking. And so, maybe I'm getting overly giddy, but I always thought this was just a cool way to visualize. That's what the interval convergence is all about. This is where we're getting actually a nice, well-behaved function defined when we treat that power series. And outside of that interval, stuff's getting kind of crazy. We really can't find a single function outside of that interval. So, all right, I'm going
Very
to
cool.
turn it back over to you.
Okay. Thank you, Tom. All righty. Here we
Hopefully
go.
that pass off works. Okay, great.
Here we go. Thank you. Very cool. Let's take a look at 2 more and then maybe we can go back to technology here. So this is an interesting one in C. This power series is centered at what we usually say A equal 3. It's got a 3 to the n in the numerator. It's got an n plus 3 factorial in the denominator. I'm going to start in the same way. I'm going to take a look at the absolute value of that ratio. And again, I'm doing the same thing. I'm taking a look at the denominator, taking the reciprocal and multiplying. And let's see here. I've got an extra 3 up here in the numerator. There it is. This n plus 4 factorial, remember, I'm going to scribble a little bit up here. Remember that n plus 4 factorial is really n plus 4 times n plus 3 factorial. So there's a lot of canceling there. And I'm left with an n plus 4 in the denominator. And I've got an extra x minus 3 in the numerator. And I'll do the same thing here. As I did in the previous two problems, this term is positive, so it passes freely through the absolute value symbol. There's sort of my simplified absolute value of that ratio. Now I'm going to look at the limit as n goes off to infinity, and this one's a little different than the previous ones. This again is constant as n increases without bound. And what happens to this expression? Well, this time there's a constant in the numerator and an n plus 4 in the denominator, so that as n increases without bound, the denominator increases without bound and forces the whole fraction to 0, and 0 times this quote unquote constant, darn it, is 0. Well, I added in a little extra here just to remind myself, since 0 is less than 1, that means that this power series converges for all values of x, because no matter what the value of x is, this limit turns out to be 0, which is less than 1. Therefore, it's absolutely convergent and therefore convergent. So, real quickly, the radius of convergence we usually write like that. I know some of us have issues with writing something as equal to infinity, but that's pretty common notation, and we as mathematicians understand that one. And the interval of convergence would be minus infinity to plus infinity, or all real numbers. So that's a little different. I like that one. Let's take a look at D if we can. I think I've got a part D in here. Yes, here we go. All right, so this has got a 3 to the n in the numerator and x minus 4 to the n in the numerator. So this power series is centered at a equal 4. There's a square root of n plus 1 in the denominator. And don't let me make a mistake on this one, Curtis. I'm going to start out in the usual way. Here's the absolute value of that ratio, reciprocal of the denominator. Let's see what happens here. I think I'm going to have an extra 3 in the numerator. Let's see, what else? Oh, I think I'm going to have an extra x minus 4 in the numerator. And I don't think I can do much with that square root of n plus 1 over the square root of n plus 2. Yes, you're right. I could write it as one giant square root. And so I did that over here with a little bit of simplification. But here's my simplified absolute value of the ratio. So by now we're getting used to this step. It's becoming part of academic muscle memory. We take a look at the limit as n goes to infinity of that ratio, the absolute value of that ratio. This is constant. That's constant. What happens here? Well, similarly, within the square root symbol, we could divide both the numerator and the denominator by n. And this inside the square root goes to 1. So the square root of that is 1. And so this limit is 3 times the absolute value of x minus 4. And as we've done in the past here with the other problems, we want this to converge, absolutely. So we set that less than 1, and we solve for the absolute value of x minus 4 because this power series is centered at 4. And therefore, the radius of convergence is right here at r equal to 1/3. All right, we're not done. We have to find the interval of convergence here. So I did a little extra step in here just for my own benefit, just to help me figure out what the endpoints are. And so what I did is I sort of looked at the definition of the absolute value. So that means x minus 4 must be between minus 1/3 and plus 1/3, just to make it easier for me to see these two endpoints that I need to check, those two values of x that I need to plug in. All right, well, I know you did this for homework, Curtis. This is a little painful, but I plugged in the x equal to 11/3, and I did a little bit of simplification, and I came up with this expression. And I believe that one converges by the alternating series test. I think the terms go to 0 as n increases without bound, and I believe the terms decrease, the positive terms decrease. And so that converges by the alternating series test. I'm going to plug in an x equal to 13/3, and this time I got Oh boy, how about this one? This is a nice problem. A 1 divided by n to the 1/2, and we recognize that as a p-series, and that diverges because p is equal to 1/2. So this might look a little cumbersome, but the interval of convergence here would be closed on the 11/3 end and open on the 13/3 end. There's the interval of convergence. Hey, 4 really cool problems to start out with. I think Tom is going to look at a little bit more technology, and then I'll try a couple different ones.
Okay.
There you go.
All right. Okay, well, what I'm gonna try and do, and hopefully this is coming up, I'm just going back to the Inspire again to look at a couple more, just pretty much in the same way we did before. So these are the next couple of power series that Steve looked at, though you notice again, I replaced the infinity with K. Part C, just wanted to make a mention, you see that n plus 3 factorial in the denominator. You see a 3 to the n in the numerator, that's going to grow pretty fast. But n factorial is going to beat it every time, because 3 to the n, we're multiplying by 3 repeatedly. N plus 3, we keep up in the n. At n plus 3 factor, it's just going to get bigger and bigger and bigger. That all said, though, this one was kind of interesting to look at graphically, and that's what I'd like to do next. So on the next page here, I put in that C of x as our F1. And I think, Steve, this was the one that this converged for all real numbers, the entire
Correct.
line.
Correct.
But as I increase the K value, see a quartic, cubic, we see this different polynomials, but man, I'm not getting that sense of
Yeah.
convergence really. In fact, it kind of looks like it's converging for a much smaller interval. So,
Yeah.
and I think that's owing to the fact that you do have that 3 to the n, and so for small n, it's really competing pretty well with that n plus 3 factorial. Well, something you can do with a slider here is, I had my slider set just to go up to 20, but I can override that and just put in my own value. So I'm going to put in 200. So this would be the first 200 terms of that power series, and take a look at what's that polynomial look like. It's taken a while. I think this will work.
Oh, how about that?
Interesting. Yeah, so I just found this fascinating, is that, okay, now this thing does seem to be settling down for a lot more values. However, once I get past x equal 4, it still looks like it's taking off. So I think here, this thing is, depending on the value of x you put in, every value of x you stick into that power series or substitute in, you will get a convergent series. But for some, it'll converge slower than others. But they all do converge. So I'm going to believe you, Steve, that it's all real numbers, but it's a little different here. So I'm going to set this back to 1 and look at that last power series. That's, whoops, I don't want to do that. That's going to be too weird. Okay. All right, let's just set it back to 1. And I'll just take a quick look at it. Remind ourselves what we were looking at. Okay, it's this one here, d of x. Yep. This is one where you had the 3 to the n. This time it was x minus 4 to the n, and you had a square root of n plus 1 in the denominator. So let's take a look at that graph. And I'll change my f1 of x to d of x. And now let's just take a look at what happens as we increase k. Wow.
How about that?
Now, if I'm remembering, boy, this is really coming home. I think your interval on this one, Steve, is like 11 thirds to 13
Yes.
thirds, which is
Correct.
like 3 2/3 to 4 1/3. Look at that. That's how tight that interval of convergence is. It's very tiny. And then once you get outside that small interval, it's taken off on us really fast. But again, I found this it's reassuring. It gives me some sense. Okay, yeah, I think that interval of convergence is making sense. So I think it's just a cool way to graphically look at these. So I'm going to turn it back over to you, to Steve. But
Okay.
After your next problem, I'll take a look at doing something similar like to this on the TI.
Okay.
Okay.
Very good. Sounds great. All right, Curtis, here we go. Beautiful. All right, so question number 2 has several parts, and it starts out with the first part A here is very similar to what we've done in number 1. We have a power series given by this expression, and it is the Taylor series centered at A = 1 for a certain function f. So we're told that. So the first thing we're going to work on is to find the interval of convergence for this power series, and we're going to proceed in the same way we've kind of set you up for this by looking at problem number 1. We start out by looking at the ratio, the absolute value of that ratio, a sub n plus 1 over a sub n, and the usual. We take the reciprocal and multiply. And let's see, with a little bit of simplification here, I think I've got an n over n plus 1. I think I've got a lonely 2 up there in the numerator. And those pass freely through the absolute value, but I keep the x minus 1 there within the absolute value. And then, as usual, I take a look at the limit as n goes to infinity of that absolute value of that ratio. So this is constant too, and this, okay, pretty common. I know that most students have seen this one. That goes to 1, divide top and bottom by 1 over n, or divide top and bottom by n, excuse me. And so there's my limit. We force that to be less than 1. We know that this is a Taylor series centered at a = 1. So we'll solve for the absolute value of x minus 1. We see that the radius of convergence is 1/2. All right, so we're almost there. And again, to make this a little bit easier for me, I'm going to write out by definition of the absolute value. I'm going to write this inequality to make it easier for me to get to the endpoints, which would be 1/2 and 3/2. I'm going to plug each one of those in, and sparing you a little bit of the details here, I think I ended up with a minus sign out in front, but the harmonic series. So I didn't add anything in here for y, but we would probably ask students for a reason. So this diverges for several reasons, or 2 reasons anyway. A student could say it diverges because it's the harmonic series. They could say it diverges because it's a p series with n = 1. So I'll just add in for completeness in here that it diverges because I recognize that as the harmonic series. And how about this second one here, where that x = 3/2? Well, now I've got a minus 1 out in front with a 1 over n. Well, this converges because, well, it's the alternating harmonic series, or converges by the alternating series test. So let's see, this time, the interval of convergence is open on the 1/2 end and closed on the 3/2 end. Pretty cool. Now, we've got several questions on this one. Tom, before I hand it back over to you, let me see if I can get a couple more of these done. So this part B is an interesting one to me. It says for n greater than or equal to 1, let's see if we can find an expression for the nth derivative of f at 1 in terms of n. So I had to think about this one a little bit. I wasn't quite sure how to attack this, and this is what I tried, and you may have a better way to do this than me. What I did is I first tried to write out several terms in the Taylor series. That's this line. And I know if it's the Taylor series for this function f, I know that this coefficient a sub n out in front must be equal to the nth derivative of f at 1 divided by n factorial. And remember, this is what I'm trying to find an expression for. So that means that the nth derivative of f at 1 is a sub n times n factorial. Okay, so let's see. So that means, let's see, there's 2 out in front here. Let's see, f sub 1, the first derivative of f at 1 has got to be 2 times 1 factorial. Okay. The second derivative has got to be this expression right here times 2 factorial. I'm looking for a pattern, sometimes hard to discern. The third derivative has got to be 8/3. Whoops, I'm sorry, right here. 8/3 times 3 factorial. Here's the fourth derivative. It's got to be this expression times 4 factorial. And finally, I think I'm beginning to see some sort of pattern to emerge. And okay, there's a little bit of a leap of faith here, and there's a little bit more problem solving in here, and a little bit more checking and guessing. And I think I finally ended up with -1 to the n minus 1. There's a 2 to the n in there. I think we can see that appearing. And all of that times an n minus 1 factorial. So that's kind of a cool problem. There's some neat, I think, problem-solving techniques in there and pattern recognition. Okay. C says, find the Taylor series for f evaluated at this argument, 1/2 x plus 1/2, centered at a = 1. So I'm first going to think out loud here. How do I solve this problem? So I believe what I need to do is I need to take this argument, plug it into the Taylor series, and try to manipulate the Taylor series so that I end up with an expression that has a summation that has that x minus 1 term to the nth power. So I tried that, I plugged it in, and I'm lucky here. Some nice things happen. I did a little simplification inside here, and I ended up with this expression. And as I stare at that, I see I can factor out a 1/2 out of each one of those terms. I can bring out a 1/2 to the n, therefore. And there's some nice cancellation here. And I think I'm left with this expression. And that would be an expression for the Taylor series for f of 1/2 x plus 1/2. That's kind of a neat, I think, AP Calc exam question. Oh, there's more. There's more parts here. So let's suppose that I know that f of 3/4 is minus the log of 2. Let's see if we can use the first 3 terms of the Taylor series to approximate minus the log of 2. Well, here are the first 3 terms. How did I get those? Well, I went back to the original series, and I just looked at the first 3 terms. There's my Taylor polynomial of degree 3. So minus the log of 2 is equal to f of 3/4, which we were told. And that's going to be approximately equal to the 3rd degree Taylor polynomial evaluated at 3/4. Now, a couple of things here, okay? This is one of the places on the AP exam where we tend to be picky about equal signs versus approximation symbols. And so you want to be careful here if you're writing something like this. F of 3/4 is not equal to this Taylor polynomial. It's an approximation. It is approximately equal to that p sub 3 evaluated at 3/4. Second thing, if we were asked to use the first 3 terms, if this is the way the problem was worded, just find this Taylor approximation using the first 3 terms. Stopping right here would receive full credit because that is a final numerical answer and it does not need to be simplified. Now, I did so because I wanted to see what was going on here. And I ended up with a minus 2/3. And that's a minus 0.667. And if you think about, I know you know what the log of 2 is equal to, and therefore minus the log of 2, that's not bad. It's pretty close. Find the first three terms in part E here and the general term of the Taylor series for the first derivative. Well, how do you do this? You take the derivative term by term. So let's see if I've got this correct here. There are no x's here, no x's here. They're treated as a constant. I use the power rule on this. I bring the n down, subtract 1 from the exponent. And then what I tried to do here, I think, was a little bit of simplification. What happened here? Well, the n's cancel. And I'm left with this. And what I tried to do here was I just tried to rewrite this giant summation starting at n equals 0 rather than n equal 1. And I think I did that correctly. I think I need to add 1 to those n exponents to make that work out. And so I think that's the expression that I worked out, that I ended up with. And it actually says find the first three terms and the general term. Well, the general term is in here. And here are the first three terms, in this case, when n is 0, 1, and 2. Cool. All right, f. There is a function g, so that g prime is equal to f of x and g prime of 1 is equal to 2. Let's see if we can find the fourth degree Taylor polynomial for g. Yikes, centered at a equal 1. Well, in order to do that, we're going to have to do a little integration, and I'm thinking ahead here. I'm thinking out loud. If I want the fourth degree Taylor polynomial for g, I'm going to have to start with the third degree Taylor polynomial for f, so that when I integrate, I'll get a fourth degree. And so I did that. Here's my first three terms up here. So I integrated term by term, and don't forget the constant c. I know, or I'm given that g of 1 is equal to 2, or when I plug in a 1, those three terms disappear. They are all 0. That tells me that that constant c is equal to 2. And therefore, here is the Taylor fourth degree Taylor polynomial for g, centered at a equal 1. Now, one more question here that we didn't ask, but we could have, and this is a good one to think about, and then I'll turn it over to you, Tom, for some more technology, is we started out this problem by finding the interval of convergence for this function f. And here we've taken a derivative, and here we've actually integrated to find this function g. I wonder what the interval of convergence is for f prime and for g. Now, that's something that we'll leave as an open question, something for you to think about. And I'll turn it over to you, Tom, for a little bit more technology.
Okay.
There you go.
All right, I'm going to shift platforms here a bit and actually go over and take a look at the TI-84. And maybe wondering, can you do these similar idea, this kind of partial sums of power series on the 84? The answer is yes. And I just wanted to illustrate how to do that with this number 2 that Steve was looking at. First of all, let me just kind of show where you'll find some things that'll be of use to you. What I found useful here was actually under something called the list menu. So I'm going to go to the list menu just to show you where you can find these things. The list menu has where you can find the names of your built-in lists. I'm going to move over here to operators. And these are operations that you can do on lists. And the two that are really helpful here for doing these power series is sequence. So you can think of these as the sequence of terms in your power series. And cumulative sum, that's number 6 here. What cumulative sum does is it takes a list and then makes a new list where each entry is the sum of the terms in the original list up to that point. So the first terms are the same. The second term of cum sum is the sum of the first two terms of your list. And then the third term is the sum of the first 3, then the sum of the first 4, and so on. So how do I make use of that? Well, let's quit out of here and go over to the y equals menu. And you can see I'm using that cumulative sum of a sequence. And the sequence, let's see if I can scroll over here so you can see more of it. It's actually the sequence of terms defined by Steve's power series. Notice it has an X in it. There's that X minus 1 to the n. And just like I did before with the power series partial sums on the TI-Nspire, notice I'm going to sum these from n equals 1 to k. And what we'll do is we'll just store different values of, we can store a value for k and then look at the graphs. Now here's what's really, really cool about this. Let me show you something here now. So I'm going to quit the y equals menu. And I'm actually going to store 3 into k. And what's really kind of cool here is you saw that my y1 was the cumulative sum. Well, that's actually a list. So when I graph y1, it's not only going to graph, it's actually going to graph the 3 functions represented by the first term, the sum of the first 2 terms, and the sum of the first 3 terms. So let's take a look and see how that looks. So I'm going to graph. And we should see, I hope. Here's the first term. It's just a linear. Second term of a cumulative sum will actually be a quadratic because it'll be the sum of the first 2 terms of the power series. And then the third function that comes up should look like a cubic.
How about that?
It's really quite slick. And let's see if I'm remembering the interval of convergence was like from
one half to 3 halves.
1/2 to, oh, look at this. So you can see kind of that tightness.
Yeah.
1/2 to 3 halves, and then it kind of gets crazy outside of that interval. Here's another thing you can do that I think is really nice is I'm going to go back to the calculator screen. I'm going to go actually store 10 in K. And don't worry, I'm not going to graph 10 things, but if I did graph Y1 again, it would actually show me the first 10 graphs up to the 10th degree. But what I want to do is I just want to evaluate Y1 of, see, Steve, I think you looked at Y 0.75, is that right? 3/4?
Yes, that's correct.
Yeah, I think you actually evaluated
At 3/4. That's correct, Tom. Yeah.
So I'm going to look, if I evaluate Y1 of 0.75, it's actually the first 10 approximations to Y1 of 0.75 that I'll get out. I mean, well, I should refer to approximations to Y1. Y1 is a sequence of these approximations. These are the approximations to your actual function. That was a power.
Mm-hmm.
Now, this is showing it in a list in this form, but let's go ahead and store that into L1, the list, and then we can look at it in a nicer way. So L1 is a built-in list. And if I go to the stat menu and do edit, here's L1. Now I've got a lot of other lists you can ignore, but these are the approximations. You looked at the third approximation.
Yes,
I think it was negative 0.667. There it is.
Yep.
Now I've got the fourth, the fifth, the sixth, the seventh. And it looks like it's converging to about negative 0.693, which is pretty darn close to the negative natural log of 2. So I think it's just a really cool way to, I think, explore. You have to do a little bit more gymnastics on the 84, but it's really pretty handy. And I found this cube sum and sequence combination is kind of a fascinating way to get at that. get these approximations. All right, let me stop the share there and turn it back over to you.
Well, Curtis, I
Hey,
think
Tom, I would, why don't you start sharing again just a second?
Oh,
At the risk of running over time just a little bit, I know we
okay.
are. But you had done those really nice sort of slider buttons, the first problems tonight.
Yeah.
So if you would go back to your y equals menu there, or your
Okay.
y equals. And
Okay.
you can either leave that in Y1 and turn it off, or you could just write over the top of it, whatever you want to do.
Okay.
So in Y1 or in Y2, wherever you're going to do this.
I'm going to leave this one in there, but I'll just go to
Okay.
Y2.
That's fine. Let's
And
go
I
to
turned it off so we won't graph it again. Okay, so
Okay.
Y2.
So in Y2, let's do the problem. I think it was letter D
Okay.
from that first demonstration. So can you get the summation from the math menu?
Sure. Okay. So I'll go in the math menu and so there's number 0 is summation.
Yep, number 0 is the summation.
Okay.
You've got that math template there, so you can do n. You can use n. So you can do alpha n
Okay.
equals 1, and then in the top, let's go up to. We can't use the letter K, but we're going to be able to use the letters A, B, C, or D. So let's use A, just because it's
Okay.
something. Make a variable name there. So let's make that A. And then let's go ahead and enter in the summation that problem, which I think, if I remember right, you have a fraction, right?
Right.
So you can use the fraction template.
Which, let's see, the quick way to that is
Do alpha x t theta n.
alpha D.
Alpha x t theta n.
Oh, sorry, gotcha.
Variable key, yeah.
There we go. Excellent.
And then just type in, I think it was 3 raised to the n. Is that right?
yes, 3 to the n.
3
and
to the n multiplied by x minus 4 to the n.
Right.
All right, just give me a little bit of time here to get that
To
all.
open parenthesis, yeah. And I thought this was really cool when I tried it just a minute ago. I thought, boy, I got to make sure that everybody can see that you
Okay.
can do this. So
Raise to the n.
raise
Yep.
that to the n, and then over the square root of n plus 1.
Right. Okay, now we can get the square root.
Now, everybody's probably wondering, hey, if I hit graph right now, nothing's going to happen, right? We got A is stored as, it is a variable. It's got 0 stored in it. N has got, we got a mess here. But if you choose the apps key, hit the
Okay.
apps key for me. And down at the bottom, there's an app that not a lot of people know about. It's the transformation graphing app. Which allows you to use the variables A, B, C, and D in transformations of functions or that sort of thing. Well,
Okay.
we're going to do that, but with the letter A here in this summation. So go ahead and start transform.
All right.
You'll get a little deal here for that. Now, I don't remember what your window was, what your window settings were.
I think it was just the standard decimal window, Zoom decimal window.
Zoom decimal. Okay, so hit Zoom decimal then.
Okay.
Zoom, yeah, hit it again. There you go, Zoom 4. And you're gonna need to change the value of A. Well, I guess you don't have you'll have to go back to the window settings. I did it with just the standard window, not the Zoom decimal window. Change the settings. So arrow up and over to settings, and let's make sure that A goes. Let's get us some decent steps. Let's set A to +1.
Okay.
not going to work very well if we have negative up there. So let's set that to A as +1 and now hit graph.
All right.
I forgot it would do that with your Zoom decimal. It would kind of jump to a bizarre setting, but you should get the linear here pretty quick.
There it is.
And then if you hit the right arrow
Okay.
and increase the value of A, now you're going to be able to get that quadratic. It'll take a second, but you'll get that quadratic just like you were doing before with that button. On the handheld, it's a little bit faster than software, but
Got it. Okay.
now you've got that same ability that you had on Inspire. If you keep going, you'll be able to do that.
Okay, I just hit it again so I could get the cubic.
Get the cubic.
Yeah, what's nice here is this is showing them one at a time.
One at a time rather than getting them all at the same time.
Yeah. Okay, yeah. Yeah.
So I figured I'd try it and see if it worked, and it did. So I thought,
Yeah, no, I see what you're talking about. No, that's a neat use of that. Okay. Very cool.
Anyway,
I learned something new too. Okay.
Thought that was a cool one. So Lauren, if you're still watching, it looks like you've got homework to show this to Mr. Beck's class tomorrow. He put that in the chat to make sure that Lauren would share that with the rest of her class there. So just set
Very
me
cool.
up. So anyway, I wanted to just thank you guys. Thank you, Tom and Steve, for this this spring. We've had a great series of talks, and thank you to everyone who's been checking in and logging in on a regular basis. It's been great to have you guys kind of building a community, and thank you especially to those students who have been logging in and asking questions, making comments. If you are looking for the professional development certificates, you can email me. My email address, I'll put it in the chat here real quick, curtis@ti.com. Please email me about that. And then finally, we are looking for topics or ideas that you might have for us to cover in the fall sessions. We'd love to hear from you, so you can certainly send your comments my direction. There at my email address, curtis@ti. Otherwise, thank you guys very much. Students, good luck on the exam.
Good luck.
And
Yeah, good luck.
we will see you guys back here in September.
Terrific. Thanks, Curtis.
Good night.